Okay, YouTube, this is my third video in my module on either inconsistent or consistent dependent systems, in which we're going to continue to focus on systems that have infinitely many solutions, but also focusing on systems that we refer to as non-square systems. So you'll notice it says here, up until this point, we've encountered only square systems, and essentially a square system is a system in which the number of equations is equal to the number of variables. And so we say that in a non-square system, the number of variables differs from the number of equations. And in this example number 3 here, it says that we have 2 equations and 3 variables. You can see that this is a non-square system because I guess if we were to have a square system, that is to say, I'm just kind of making up a third equation here, x plus y plus z equals 1, then you could see that this right here over here on the left, we would have 3 equations, 3 variables. We could see that this is kind of a 3 by 3 arrangement. And so when we have non-square systems, we're essentially referring to a system that if you were to look at the left side, it would either be, I guess, tall and skinny, that is to say you would have fewer variables but more equations, or you could have very few equations but a lot of variables. And so with these non-square systems like these, what we're going to see happen quite a bit of the time, especially when we have fewer equations than variables, is that we're going to get an infinitely many system or infinitely many solution case system. And the reason why is because recall that if we were to graphically represent these 2 equations here, they both represent a plane in 3 dimensions. And so if we were to look where these 2 planes intersect, we could say, well, then they intersect along, say, this entire set of values right here, these order triples along this line. And so that's why we're going to end up with infinitely many solutions. My job here is just to show you how you would go about solving, I guess, a system that has fewer equations than variables. So the first thing we would do is, obviously, we would drop this into an augmented matrix. Let's go ahead and do that. And so we'd say our augmented matrix, we're going to use Gaussian elimination on this as well. And so one thing to go ahead and foreshadow is that we want a 1 in the top left corner here of our matrix. And we already have a 1 in the bottom left corner. Our 2 options essentially are we could take the whole first row times a third, which is going to create some pretty heavy fractions with these remaining values, or we could just switch row 1 and row 2 around. So that's the option I'm going to take here, just to get a 1 in the top left corner. So we're going to go ahead and write our row operation here. We say row 1, what it did was we switched it with row 2. So we get a 1, a 2, a 1, and an 8. And our second row here would be a 3, a 7, a 6, and a 26 here. So essentially what we're going to do now is we're going to use that 1 to get rid of the 3 below it. And so as is the typical method here, we're going to take 1 times the opposite of the number, multiply it by the opposite of this number we're trying to cancel out, and then add it to that number. So in other words, we're going to take negative 3 times that row 1, but then we're going to add it to row 2. So row 1's the same. We have a 1, 2, 1, and an 8. But here we have now a 0. We could say negative 3 times a positive 1 is a negative 3, and negative 3 plus positive 3 is a 0. Now if we take negative 3 times this positive 2, we get a negative 6, and negative 6, when we add it to this positive 7 here, gives us just a 1. Negative 3 times a positive 1 is a negative 3, and negative 3 plus a positive 6 here is a 3. And then negative 3, if we were to take that now, times 8, we would get a negative 24, and negative 24 plus 26 here is a 2. So you see what we end up with here. Basically, we've got a 1 on the top left, and then we've gotten zeros underneath. Now the next step would always be to get a 1 here, but because there is already a 1 here, since there's nothing underneath to use that 1 to cancel out, then what we're going to say is that this is the best I can get this into what we call row echelon form, with 1s down, I guess, the main diagonal, and 0s underneath. So if that's the case, what I'm going to encourage you to do is rewrite the system associated with these, I guess, this augmented matrix here. And so if we have 3 variables, I'm going to assume they're x, y, and z. We have x plus 2 y's plus a z in our first equation is 8. Our second equation becomes y plus 3 z's is equal to 2. And so looking at this, we're going to do very much the same thing that we did when we solved systems that were dependent, which this is a dependent system. But we're going to say, let's let or allow one of our variables, most typically z is what I go for, we're going to allow it to equal a parameter a. And so what we could say then is that our solutions, essentially, we know that we have x, y, and z, and that our z value is equal to a because we set a z equal to a. So now that we know what z is, let's go ahead and plug this back into our original equations here. We'd have y plus 3 times a, really, is our z value here, is 2. So in other words, if we were to subtract 3a from both sides, then what's going to result is that y will be equal to negative 3a plus 2. I'll put a box around this here, and I'll go ahead and put this up here. We would say then our y value is negative 3a's plus 2. Okay? And then we would say, now that we know y and then we know z, let's go find x. We would say, well, if x plus 2 times y, and I'm just getting this from the first equation up there, plus a z is equal to 8, then if z is equal to a, and we've discovered that our y value is negative 3a plus 2, then cleaning this up here and solving for x, we would get x looks like negative 6a plus 4 once we distribute our positive 2 here, plus another a is equal to 8. As we combine our like terms here, we would get x minus 5a's plus 4 is equal to 8. And then what we're going to do is we're going to add 5a and subtract 4 from both sides, 2 and from both sides. So we would get basically just x then would be equal to 5a's, and then this 8 and a negative 4 here would combine out to be a positive 4. So I'll put a box around this here. We would get 5a plus 4. So we would say, okay, well then our z, or our x value here, x value is equal to 5a plus 4. And these would be all infinitely many solutions to this case here. So what I want you to do is, as usual, go ahead and pause the video and try this next one on your own, but when you're ready to look at the solutions, then go ahead and unpause the video here. So to bury this example, let's go ahead and take a look at what I would do here. I'd go ahead and write my augmented matrix. We have a 1, 2, 3, and a 70. Okay, it looks like here, and we have a 1, 1, 1. That's kind of neat. 1, 1, 1, and a 60. But we have fewer equations than variables, so we can go ahead and be suspicious that we're going to get infinitely many solutions is our solution case here. And so looking at this, we already have a 1 in the top left corner, and we want to get rid of the 1 below it. Let's do this. Let's go ahead and take the 1 in the top left corner times a negative 1 so that we cancel out with this positive 1. So we'd say negative 1 times our row 1. We're going to add that to row 2. So what we get is row 1 is the same, 1, 2, 3, and then 70. And then here we would have a 0. Now negative 1 times a 2 is negative 2, and negative 2 plus a positive 1 is a negative 1. Negative 1 times a 3 is negative 3, and negative 3 plus a positive 1 is a negative 2. And then we would say negative 1 times a 70 is negative 70, and negative 70 plus a positive 60 is a negative 10. So the interesting thing here is this: we could actually go ahead and set the system back up, but what I want you to know is when we're doing something like this, I still want you to follow the rules of Gaussian elimination, which would mean that once you have a 1 in the top left and you get zeros underneath it, the next thing we want to do is get a 1 here. And so it does require that we go ahead and take the whole second row times a negative 1, but that's okay. That's not a hard thing to do. We have a 1, 2, 3, and a 70 in our top row. And our second row becomes the opposite of what we had before, so 0, positive 1, positive 2, and a positive 10. But our system then that is associated with this, we could not Gaussian eliminate any further than what we have already done. We'd have x plus 2y plus 3z's then would be equal to 70. And then our second equation would be y plus 2z's equal to 10. And so with this here, with fewer equations than variables, we're going to get infinitely many solutions likely. Okay, that's likely the case. So since I do see that we do end up with this here, let's go ahead and start by saying, well, then our solutions, let's pick one of our variables here, x, y, or z, to equal some parameter. And so I'm going to say let's let z equal a. And so what this is going to mean is then our solutions, the z value is already equal to a, and that's set in stone. So what we want to do is go back and find y. Well, if we know y plus 2 times z, which is really 2 times a now, is equal to 10, then subtracting 2a from both sides of this equation here would result in y being equal to negative 2a's plus a 10. So I'll put a box around that. I'm also going to write this up here. We have negative 2a, negative 2a. Let's just get rid of that altogether. Negative 2a plus 10. And then we would say, plugging this back into the first equation with our z being equal to a, we would say x plus 2 times y plus 3 times z is equal to 70, where z is equal to a. Y is equal to negative 2a plus 10. So let's go ahead and clean this up. We'll distribute first. We have x minus 4a's plus 20 constants plus 3 more a's is 70. Combining our a's now, looks like we have x minus a single a plus 20 is equal to 70. And if we were to now add a but subtract 20 from both sides, we would get that x has to be equal to a single a, and 70 minus 20 here would be 50. So we would say that our x solutions with respect to a would be a plus 50, and here would be all infinitely many solutions to this consistent dependent system here. Cheers.